Okay. Next stop, we'll have Professor Wang. He's an assistant professor at USC CS, leading the Geometry, Vision, and Learning Lab. His research focused on using machine learning to enable robot intelligence with minimal human supervision. Professor Wang, could you share your screen, please?
You guys see my screen?
Yes, we can see it.
Oh, nice.
Yes.
Should I get started?
Yes. Yes, please.
Oh, okay. Hello, everyone. My name is Wang, and I'm an assistant professor at the USC. I'm super sorry I couldn't make it in person to Hangzhou, also because of a visa issue. But I'm very happy today to share our recent works on robot learning from any data. So in the past few years, we have been seeing a capturing explosion of robotics. For example, nowadays you can take a Waymo self-driving car in downtown San Francisco, Bay Area, Los Angeles, Phoenix. And as we all know, with Unity, it's a humanoid robot, so you can play very fancy Kung Fu style motion, and this was never possible before, like several years ago. And also, driven by robotic foundation models, you can also enable these robot arms to perform highly fine-grained dexterous manipulation tasks. So what lead to this success? So to me, there are three major driving factors that lead to such development. So the first one is hardware. So in the past few years, we have seen a lot of great hardware companies that produce highly dexterous, agile robots that can perform very hard, very challenging robotic tasks, such as humanoid quadruped or or robot hands. And on the algorithm side, we have been learning lessons from machine learning and the computer vision literature. So we develop robotic foundation models based on VLMs, based on recent generative models, such as the diffusion policy that leverage diffusion models to model multi-model behaviors for robotic manipulation. And most importantly, on the data side, we have been developing very good data collection or generation tools such as simulation and the real-world data teleoperation system. So on the left is NVIDIA's ISAC SIM platform. So with ISAC, you can render robotic data in parallel. You can even generate robotic data, generate 1,000 or even 10,000 robotic demonstrations in parallel on a single GPU. So this significantly unleashes the power of robotics. And also on the right is Berkeley's Jello teleoperation system. So with this teleoperation system, you can, or as humans, we can collect data from the real world. We can perform the very challenging tasks with this Jello teleoperation system. And to me, data is the most important factor. So why is that? If you look at the trajectory of artificial intelligence in the past few years, you will realize that data is the most important key to AI. So taking computer vision or visual recognition as an example, so before deep learning, if we want to tackle a visual recognition task, usually what we do is we use handcrafted features such as hog features, followed by simple classifiers such as SVM to tackle this task. And this requires little data or even no data. As you can imagine, the method performs not that good. And later on, with the introduce of large-scale curated dataset such as the ImageNet, so we have improved the performance of convolutional neural networks. So nowadays we can train convolutional networks to perform certain visual recognition tasks better than humans do. And further, as we all know, transformers, which are more data hungry and more performant, are trained on web scale data, and nowadays can perform much better visual recognition tasks than humans. And very recently, so we have developed vision language models, foundation models that are trained on multi-model dataset. And these vision language foundation models can perform visual recognition and the visual reasoning tasks, tackling a broad range of visual perception and reasoning tasks. So what about the physical AI? How can we collect enough data to enable all these physical AI tasks? And how can we make sure to collect the right data to solve those physical AI tasks? So these are the problems we are trying to tackle in my group. However, if you look at this physical AI data collection problem, it's actually much harder than a single image annotation problem. So if you look at this image annotation, annotating a single image takes less than 1 second, and this annotation platform is ubiquitously available all over the world. So as long as you access the internet, then you can help annotate the data. And as a result, the per data point cost is less than 1 cent. So this is pretty cheap. However, if you look at this physical AI or robotic data collection, so even for a single very simple robotic task, this takes more than 60 seconds for the human to teleoperate the robot to perform the task. And also what is more important is that this is confined to lab environments, meaning that you have to basically set up the robots first before you collecting the data. So this is not accessible everywhere in the world. And as a result, the per day point cost is about $5 for a single trajectory. So this is a huge difference between this physical AI data collection versus image annotation. So now the question is how to generate those robotic data with some spatial intelligence, computer vision techniques to really bring down the cost from 60 seconds to 1 second and the $5 to 1 cent. So this is a problem we are trying to address today. And I would like to argue 3 directions that we can explore to reduce the data cost to generate robotic data with minimal human supervision. So the first one is use real-to-semi reconstruction. So if we can convert a single image into a robotic demonstration, that significantly improves the accessibility of robotic data. So in that front, I will talk about our recent paper called Robot Learning from Any Images. And we try to convert a single image from the internet to a robotic demonstration to learn some robotic imitation learning policy. And the second direction I would like to argue is that we should leverage human data. So similar reason, so human data is everywhere available. And if we can convert those human data into some demonstrations for training some models for humanoids, for example, then we can greatly improve the skill of robotic, especially humanoid dataset. And then finally, I would like to argue that even though we have a lot of in-the-wild data or synthetic data, we still need a better teleoperation data to really align the robotic action space to the right robot. So in that front, I will talk about our recent effort to collect a large-scale, high-quality humanoid manipulation dataset called Humanoid Everyday. Without further ado, let's jump to the first work I would like to introduce, robot learning from any images. So this is an overview of this work called ROLA. So what we do is we take an image from either the internet or from the real world captures. Then we add a robot and the demonstrations into the image, and so that it can be a robotic demonstration that can be used to train robotic foundation models. And we can create millions of such robotic demonstrations from in the wild images. So how does ROLA work? And let's dive into the details of the pipeline. So basically this work consists of 3 major steps. So the first step is try to recover the physical scene from a single image. And this image again can come from a wide range of sources, including real-world camera captures, existing robotic datasets, or even internet images. And we began by obtaining texture mesh for both the objects and the background, so which recovers the scene geometry and appearance. So we first generate object segmentation masks from just using the grounded segmentation models. And for background modeling, we use an image imprinting model to synthesize a background-only image, which is used to texture the background mesh. And to further estimate the background geometry, we use metric depth estimation models to infer the background point clouds. And then we try to lift the 2D images from to 3D scenes. And basically, each segmented object is passed through an image to 3D model, and this model will generate textured object mesh. And for the background mesh, we use a surface reconstruction from point clouds to generate the mesh. And once we recover the 3D, we need to recover the full scene configuration, which includes both the object scales, poses, and the camera pose. So we first apply plan estimation on the scene point clouds to estimate the ground normal and align with the gravity so that we can recover the camera orientation. Then we use a point cloud registration to align each object mesh to the correct size and the pose in the scene. And finally, to really enable physical interaction, we estimate some key properties like physical properties like the materials or the frictions of the object using large language models or vision language models. And then we place a robot so that the manipulated object lies within the reachable workplace. And that was step one. And then in the second step, we try to generate a scalable robotic data with the simulation. So we generate diverse robotic demonstrations using a physics simulator. So these physical simulators can be combined with direct teleoperation, script policies, or pre-trained manipulation policies to generate the demonstrations in the simulator. And to reduce the sim-to-real gap in the visual domain, we also include a visual blending technique. So we render the observations from the simulator composed with the original real-world background using Z buffering. So this provides photorealistic observations or appearance for the robotic demonstration. And in the final step, we try to learn a policy and deploy the policy using the generated data. So we use the collected demonstrations from a single image to train an imitation learning policy and directly deploy them in the real world. And then in addition, so this pipeline can also enable the scalable data creation for training vision language action models or learning vision-based manipulation prior. So here are some results. So first, we conduct real robot experiments to investigate whether the method ROLA can enable single image real-world robot learning. So specifically, we set up 2 real-world robotic manipulation tasks. So the first one is object manipulation in cluttered scenes. So the robot must pick up a banana in a cluttered environment and place it accurately inside the sink. So this is to evaluate the grasping accuracy and the collision avoidance. And then in the second task, we do pouring water. So the robot must pour the soda from a can into a cup. So this is to evaluate the manipulation precision. And the left column shows the data generated by the ROLA in simulation, while the right column shows a corresponding real-to-sim policy deployment. So as you see, even without any human demonstration, the learn policy can perform the tasks. And then we also try to show that ROLA supports a highly efficient and scalable robotic data generation from a single image. So we investigate whether this can facilitate large-scale training of vision language action models. So to this end, we collect a large amount of data by taking pictures in the real world and collect the same scale of demonstrations as existing data such as bridge data V2 in simulation. And the whole process only needs 2 hours of human labor. So this shows the scalability of ROLA. And then we learn VLA using the collected data. And we deploy the VLA, we basically evaluate the VLA using 10 simulation tasks and 4 real-world tasks. So here I show the 4 different real-world tasks that need spatial understanding, visual reasoning, language following, and concise manipulation. And the final experiment I want to show is that how ROLA enable manipulation prior learning from very in-the-wild data. So basically, we try to collect a lot of internet images, and then we try to build a data set from those internet images. And let's use this apple picking as a case study. So we collect over 2,000 internet Apple images, and we leverage ROLA to generate over 3,000 demonstrations to pick up apples from the internet images. And once the data collection, data generation is done, we pre-train a neural network to encode the images and output the 6 staff pose, grasping pose in the 3D space. So this is somehow learning the grasping or manipulation prior from internet images. And once this learning is done, we deploy the learn model directly into the real world. So basically, the model first predicts the grasping pose and then use the motion planning to complete the task. We demonstrate the deployment on apples with different colors, sizes, and poses. So here are some real-world demonstrations of these apple picking tasks. As you can see, even with different apples, the model itself is pretty robust. So to summarize a little bit, so with ROLA, we show that data quantity and diversity are really bottlenecks in scaling up robot learning. And also existing teleoperation data provide physically accurate supervision. Collecting them as skill really requires a lot of human efforts and specialized hardwares. And instead, what we should do is to leverage all those internet images and videos and to convert them into some robotic demonstrations that we can learn from. And this is basically ROLA. And after ROLA, my student Jiageng tries to think about the question whether we can leverage a video generation model to provide a demonstration instead of cross-sourcing images from the internet. So to that end, Jiageng extend this work to a new work called robot learning from a physical world model. And what we are trying to do is we, instead of using the internet images, we leverage word models such as we leverage video generation models such as View 3 to generate a demonstration. So due to time limit, I won't go into the details of this work. In high level, the pipeline is pretty similar to ROLA. So the major difference is that we use a video generation model to provide demonstrations. And here are some results of this video generation based physical world model. So the first row is generated videos from View 3, while the second row is a policy learned from the generated data and deployed into the real world. So here is a rollout. So although manipulation is a very important task, and we can leverage this in the wild data to enable manipulation. But if we want to perform more challenging mobile manipulation tasks, we need some humanoid robots. And it turns out it's even a harder task to collect data or to generate data for humanoids. So this is because compared to manipulation or manipulators, so humanoids has more degrees freedoms, and this cannot easily handled by motion models. So meaning that action generation is super hard for humanoid. So now the question is, can we derive humanoid data from internet images?
Sorry to
So to that
interrupt.
end,
Oh, we have 5 minutes left.
okay, sure. I will skip a lot of details. So to that end, we recently have a work called the UH1, learning from massive human videos for universal humanoid pose control that was led by my student, Jiageng Mao. And in very high level, this work tries to solve two questions. The first question is, can we create an automatic humanoid data generation pipeline from internet videos? So what we do in this work is we cross-source a lot of human videos, videos of a single person motion from the internet. And then we convert those videos into a humanoid motion demonstration. so that we can have a lot of data to learn a generalizable humanoid motion generation model. And the data is the first question we try to answer in the work. A second question we try to answer is that we leveraging this dataset, we learn a unified whole body control model that is based on a transformer architecture. So this transformer architecture takes in some language instruction as input and directly output the control signal to control this humanoid robot to perform a certain motion. So due to time limit, I will skip all these details. So I want to show that show the overview of the data set. So overall, we collect a lot of humanoid data from these human videos. And compared to existing one, this humanoid data set called the humanoid X is much larger than any of existing datasets. And we show diverse motions in the dataset. And on the right is an example of the data we collected. So for each data example, it contains human RGB captures, and also it has extracted human mesh, and also it has corresponding key points and humanoid control command that are transformed from the human mesh. And finally, we have the language description of the task for each sample. And I will also skip a lot of results here. And finally, I want to show a recent work called the Humanoid Everyday. So this Humanoid Everyday is a high quality humanoid dataset that is basically tackles everyday household tasks. So we use a Vision Pro-based teleoperation to collect over 260 tasks that cover 7 categories. And we create a very high quality multi-model dataset, and we cover we include the different modalities, including RGB, depths, LiDAR signals in the dataset, and also we support the perception signals, including the joint states, tactile signals, odometry, and the IMU signals. And finally, we also have the task descriptions and the human actions in the dataset. And this is a data viewer that is associated with dataset. And we also test policy learning using the dataset. So basically, we fine-tune all the open source foundation models using our foundational VLA models using our dataset, and we compare their performance on different levels tasks. As you can see, on some tasks, these foundation models perform pretty good on these simple tasks. However, on some tasks that require, for example, high precision or dexterity, so all of these models perform very poorly. So they suggest further rooms for improvement in the future for humanoid VLA. And finally, I want to share with you that associated with this dataset, we also provide a cloud-based evaluation platform. So this is try to make sure the evaluation is fair to different methods. So users can leverage this cloud evaluation platform and upload their policies to the server. So we will evaluate their policy in both simulation and in our real world setting. So this will make sure all the policies are evaluated in the same environment, in the same setting, using the same types of tasks. And this is basically humanoid every day. And due to time limit, I will stop here. And with that, I want to acknowledge all the students who did all the heavy lifting works, and I also want to thank all the funding agencies to support our research. And I will stop here. I don't know if we have time for questions. If we do, I'm happy to answer.
We can take one question from the audience. Thank you for the great talk.
Just one question, and anyone else to take it?
Sorry, is that a question?
I think Simon is collecting question from the audience now.
Oh, okay. Sorry, it's very blurry. The voice is very blurry.
Just 1 second, sorry.
Mhm.
Okay. If there's no questions, we can move on right now.
Okay, stop here.
Thank you, Professor Wang.
Yeah, thank you for the invitation.
Yes.